How self-driven robots move efficiently from point A to point B. A common problem in computer science is to design a procedure to find the shortest path between two locations. This is done by the dijkstra algorithm applied on a specific vertex. After applying the dijkstra algorithm on the A vertex, we obtain an information table like this. Here are each pathway and cost for every travel from the A vertex to each location. By example, we want to go from A to B. The cost is 3 units, and the previous vertex column denotes the previous location in order to reach B. But how is generated this information? Initially, we set all distances with infinite, and the own location with 0. Then we explore the boundaries. If the value is less than the known distance, we update both columns. This process is repeated on each vertex until have completed exploration for vertex A. Following the same basic rules for a non-directed graph, a directed graph is composed of a set of directed edges, denoted by order UV pairs, in which usually you find many ways to refer that U is the starting vertex and V the end. In fact, a non-directed graph is a special type of directed graph, where each connection is represented as a bidirectional edge like this. In a specific vertex, the number of entering and leaving connections are called indegree and outdegree respectively, being called a source or sink in effect. Again, the same rules apply for non-directed structures, except that edge directions should be coherent. Remember, a trail cannot repeat vertices or edges. A path may repeat vertices, no edges. So, a spanning path contains all vertices, and a specific vertex V is said to be reachable from U if there exists a path from U to V. There are 3 rules to classify a digraph connectivity. If it is possible go from any vertex to any other vertex, hence exists a spanning path, and it is a strongly connected graph. If it isn't possible go from any vertex to any other vertex, but still exists a spanning path, it is a unilaterally connected graph. And if transformed it into a non-directed graph, still being a connected network, it is said to be a weakly connected graph. Even if the edges directions, which are obvious, are omitted, rooted trees are into a digraph category as well. Usually the root is denoted by the R letter on the top. Also, it can be placed anywhere like this. A vertex level is the distance from the root. The tree depth is its longest distance. These are leaves, and a branch is any path from a vertex to a leaf. Now, ordered trees are browsed by their UAS or universal address system. This provides us a shortcut to reach any location. Going back to digraphs, there will be 2 structures to keep in mind. The first is its adjacency matrix that we saw before, and its reachability matrix that indicates if a specific vertex is reachable from another. By example, in this graph it is possible to go from A to C, but isn't possible to go from A to B. This seems easy, but is not. In order to do this, we have to compute the transitive closure, as we will see later. Now, referring to the n-power matrix of G is just the path of length n across the graph G. By convention, a graph with k number of vertices can have up to k power matrices. By example, the adjacency matrix denotes the direct connections. The 2 power matrix of G denotes the paths of length 2, and so on. We will not discuss this concept for now. Just keep in mind that in a very boring and long process, the union of all power matrices results in the transitive closure. So, how robots build a reachability matrix to see if a place is accessible and decide where to go? This is done via warshall algorithm. We start from the adjacency matrix. Find the cross product between first column and first row. Then the cross product between second column and second row, and so on. The process will be repeated until have covered all adjacency matrix. Finally, the set union of all elements results in the transitive closure. Now consider the case where instead of distance units, the cost of move from point A to point B represents energy units. In this way, a robot climbing a slope will require positive energy, but if the slope is negative, it will gain potential energy. It even accelerates. This can be viewed as a negative energy. In such case, you cannot use dijkstra algorithm to find the shortest path. In other words, if any negative weight exists, apply the Floyd-Warshall method, and the result will be a matrix with all shortest paths, pretty similar to dijkstra algorithm, except that instead of an initial vertex, we rely on an intermediary to compare. Both depth-first search and breadth-first search algorithms works exactly the same for directed graphs, except that the entire process is done following the edges directions. Another application of graph theory is topological ordering. Any complex operating system executes dependencies based on a prerequisite order. For example, the C process cannot be called until A, therefore G completes. Only the AG structures can be arranged in such a way. The easiest way to solve this task is following a depth-first search method by exploring the vertices one at a time and storing the exhausted ones in a stack. When all vertices are exhausted, reversing the stack results in a valid arrangement. So, we previously saw how to apply the Floyd-Warshall method to compute all shortest paths in a graph with negative weights. Sometimes we don't need all information, only the shortest paths from a single source. In this case, we use the Bellman algorithm. Before jumping to it, let's point out that this only works in graphs without negative cycles because it will enter into an infinite loop. This method is based on a sequential relaxation. Start from the target vertex neighbors. Then we do the B relaxation, update the values. Then comes the C relaxation, update the values, and so on. In simple words, if you need to find the shortest paths from a single source in a graph with negative weights, use the Bellman method. The graph analyzer is a simple application to enter any graph in the world and obtain shortest paths via dijkstra method, topological sorting, transitive closure, or shortest paths via Bellman method. The input text file must be a JSON document. By example, in this non-directed graph right here, all vertices are contained in this array, and the bidirectional edges in this other array. For example, we want to do an analysis on this graph. Let's transpose it to a JSON format. In the same way as in the example, all vertices in this array and all edges in this other. The weights are 1 in unweighted graphs. Remember to save the file with .json extension and select all files in the editor. Finally, we upload the file already created to the website, and here are the results. Question 1. Let's suppose you're in London and must deliver a payload to Madrid, having only the graph analyzer and the information of train directions going that day. Find the best path. So the structure visually looks like this. By example, we know can go that day from London to Brussels and from London to Glasgow. As you see, it's exhausting to manually compare all distances. To solve it, let's transpose the JSON format for this graph and apply the dijkstra method in the graph analyzer. Download the JSON version of the structure from this direction and upload it in the dijkstra section. Now, following the output, in order to reach Madrid, we must go previously to Barcelona, Lyon, Paris, Bern, Munich, and Brussels. A total of 20 units. Question 2. Once you're in Madrid, tell your partners who can deliver anything to you using the railway that day. The warshall algorithm will construct the reachability matrix for this structure. So let's upload the JSON file in that section. As we can see, all stations except for Glasgow can reach Madrid. Within Venice boat network, it is possible to visit any of the city islands. The 11 different locations and their respective flares are displayed in the following document. There is only one exception. A group of tourists will pay 100 euros if you serve as a helper from Lido to San Michel. Find the less expensive way to go from Camp Alto to San Michel. This is how the situation visually looks, really like. What scientists usually do is to apply a pathfinder algorithm. In this case, we are interested in just one source, so it's better to apply the Bellman 4 method. But there are multiple negative cycles, and the structure is expressed in gain terms. So let's begin with expressing the graph in cost terms. In that way, the situation is reduced to find the less expensive route. In effect, when we analyze the document, there is a gain from Camp Alto to San Michel of 50 euros. So we have to go previously to Lido, San Erasmo, Venice, Torcello, and Aeroporto. This has been all. By the way, if you want to learn from more advanced exercises, a link will be available on the video description. Thank you very much for watching our video and see you on the next unit.